Hi everyone, Mr. Boltri here, bringing you video 3.4. We're going to talk about how to draw the force diagram for a more advanced situation. So first, we're going to review the original 5 rules for force diagrams, and then I'm going to give you 5 more rules. And for each of these rules, each of the new rules, I'm going to ask that you draw a force diagram that goes with the new rules. But before I get ahead of myself, let's go over the original rules. First, it's important to show exactly what we're drawing the forces on. In this example, we're drawing the forces on the book, which you can very clearly see because it says book in the middle of my box. Next, we don't want to draw the forces on the book if we're given a picture, because then the picture will get really complicated and cluttered. We want to move over to the side and redraw the book. Except this isn't an art class, so instead of drawing the book, we're just going to put a box around it and say this is the book. So next, we're going to show the forces as arrows that start at the object and move outward. And the length of those arrows does show the magnitude of the force. So if an arrow is longer, then that shows a bigger force. And last but not least, we're going to label our forces with the by on notation, as well as the name. So this is the force normal by the table on the book. And this helps us keep track of everything, because if these are all the forces on the book, then we should never see a force by the book. And that'll be a very clear indicator that we've made a mistake. This should always be on book if we're showing all the forces on the book. Okay, now we're going to do the next 5 rules, 6, 7, 8, 9, and 10. And for each, I'm going to ask that you draw a force diagram for the situation. So rule number 6 is that there can be more than one force in any given direction. So for example, I would love for you to draw the force diagram for the forces acting on this cart. Let's say that the cart is stationary, so the forces on the cart are balanced. But you'll notice that person 1 and person 2 are both pulling to the left. So I'm going to be curious as to see how you draw that in your force diagram. And then in our next class, we're going to come together and then compare force diagrams to see if everybody got the same thing, or if there's any sort of conversation about how everybody did. So now would be a good time to pause the video and do the force diagram for all the forces on the stationary shopping cart. And then we'll move on to rule number 7, which is that normal force does not always equal weight. And weight is just another way to say force gravity. So normal force does not always equal force gravity. In this situation, up until now, we've shown several situations in which normal force does equal force gravity, but no longer is that always going to be the case. For example, I would like for you to draw the force diagram for the forces acting on this teacher as they are standing on a scale, and then somebody comes up behind them and pushes down on the top of their head. So what forces are acting on this teacher, and how is it that in this situation, normal force does not equal force of gravity? Again, I would like for you to draw the force diagram, and then we can deepen this discussion in our next class. Rule number 8 is that forces are not always entirely vertical or horizontal. So for example, let's say again that this box is stationary, has a force of gravity of 6 newtons down, and then a person is pulling it to the left and gets it to the place where it's stationary and stops. So then that means that this force tension in the rope right here is going to be partially up and partially to the right. So I'm curious how you draw that in your force diagram to allow for us to still have balanced forces in this situation as well. Rule number 9, but if the object has a constant velocity, all the forces in the horizontal and vertical have to still be balanced. So this is actually really important and gets us into rule number 9, which is that when determining whether or not the forces are balanced or unbalanced, we look at all the horizontal forces and we look at all the vertical forces separately. So something can be balanced in the horizontal direction, but unbalanced in the vertical direction. For example, I would like for you to draw the forces on this rocket ship as it is accelerating upwards, as it's speeding up, sort of launching off into space. So it's speeding up in the upward direction, and I would like for you to draw the forces on the rocket. And hopefully your forces are unbalanced in the vertical direction because it is not maintaining a constant velocity. But hopefully it is balanced in the horizontal direction, or else it might be veering off to the left, veering off to the right, or then it would crash. So that's why rule number 9 is important, because they can be balanced and unbalanced, vice versa, or balanced, balanced, unbalanced, unbalanced. Any combination of balanced and unbalanced in the vertical and horizontal directions. And the last rule is that certain forces always act in a particular direction. So I'm not going to ask that you do a force diagram for this one because we will focus a lot on this in the next class. I just kind of want you to get the basics, so make sure you get this written down. So for example, if we have a box that's on a incline, the most important thing to always remember is force gravity is always, always, always straight down towards the center of the earth. But friction, because it's in the opposite direction, sort of friction is the rubbing together of two surfaces. We can imagine that if the box is rubbing down this way, then the friction is going to be up and to the right. And so that is because friction is always in the opposite direction of the motion. So if we were to imagine that this box were to be sliding, we know it would slide down and to the left, sort of down the incline. So that means that the friction is up and to the right, up the incline, because friction is always in the opposite direction of the motion. But you might say, well, what if the box is stationary? So I always like to imagine it's either the motion or the desired motion. And by that, I mean, if friction were to disappear, which direction would the box go? If friction were to disappear, the box would go down and to the left. So the friction is acting up and to the right. And last but not least, normal force. Since normal force is the force exerted by a surface, so it has to be also in the direction of the surface. So you can see the surface is sort of at an angle. So then the normal force is going to be perpendicular to that surface because it is the surface that is doing the pushing on the object. So you don't need to draw a force diagram for this one. You just need to write down these three sort of sub rules, 10A, B, and C. And then make sure you have your other four force diagrams for rule 6, 7, 8, and 9. And then we will compare our force diagrams and do some more complicated force diagram practice in our next class, which I'm looking forward to doing with you then. If you do have any questions, make sure you get them written down. But for now, this is Mr. Boltri wrapping up video 3.4, where we talked about the advanced force diagram rules, and go Bears.